In this video, we're going to get an introduction to vectors. In particular, we'll discuss the concept of component and magnitude as they refer to vectors. We need to study vectors for a number of reasons. There are a lot of real-world quantities that we can model using both direction and size. These include things like forces, velocities, and fields, which can't be described with a single number. We'll see over time that vectors are the language of multivariable calculus. If you want a real-world motivation for studying vectors, you can think about a wind that pushes an airplane east at 20 miles per hour, or a current that's pushing a boat north at 10 miles per hour. Both of these real-world situations involve the combined effects of both direction and magnitude, and therefore require vector reasoning to understand them. In order to use vectors, we need to know what they are. A vector is a quantity that has both magnitude, or length, and a direction. There's three notations we'll see commonly for them. V with an arrow over it, a bolded letter to signify our vector, or this notation involving left and right angled brackets, V1 and V2, which we'll discuss in more depth momentarily. A particularly important kind of vector is something called the position vector. A position vector is one that's positioned with its beginning at the origin and its ending at some point P. If our vector starts at the point P equals AB, then we write the vector using the bracket notation as the vector A comma B. Notice that if we choose any point AB, and we draw a vector that terminates at that point, we'll call this vector V, and we'll denote it using our bracket notation as A comma B. Then the first component of our vector A represents the horizontal distance that our vector has covered, and the second component B represents the vertical distance that our vector has covered. We'll see that this is true for any vector, whether it is a position vector starting at the origin or it starts at some arbitrary point. We can write any vector we want in component form, regardless of whether or not it's a position vector. When we do this, each component represents movement in one coordinate direction. The first component is the horizontal movement. The second component is the vertical movement. These components fully determine the vector regardless of its starting point. In other words, we can have a whole lot of vectors that start and end at different places, but that in their component form are written identically. In this case, each of these vectors has the exact same magnitude and the exact same direction, which are the two important quantities that we're representing when we use a vector. If we consider a vector V in component form, V1, V2, regardless of where that vector is located in the plane, we know that V1 represents its horizontal distance and V2 represents its vertical distance. Then it's a very straightforward application of the Pythagorean theorem to measure the magnitude of that vector. We use double absolute value signs to indicate we're talking about the magnitude, and we can see that the length of this thing is going to be the square root of V1 squared plus V2 squared, giving us a very straightforward way to determine the magnitude of any vector positioned in the plane. Let's take a look at an example. We have the vector V equals 3, negative 4. We want to sketch this vector, find its magnitude, and then sketch two equivalent vectors. So we know by the way that it's written that this is a vector that has a horizontal component of 3 and a vertical component of negative 4. I'm going to start by drawing it as a position vector. So I'm going to say that this is a vector that terminates at the point 3, negative 4, right here. And so we know that if we draw the vector that begins at the origin and ends at that point, we can label that as the vector 3, negative 4. The magnitude of that is going to be the square root of its component squared. So we'll do 3 squared plus negative 4 squared, which is 9 plus 16. And we're going to get 5 as the magnitude of that. Now we need to write or draw 2 equivalent vectors. We can pick any point that we want as the beginning point, and we know that our vector is going to have 3 as its horizontal component and negative 4 as its vertical component. So that's 3, that's 4 in the negative direction, and so we know that this vector here is identical or equivalent to the one that we started with. Similarly, picking another arbitrary space, we're going to go 3 in the horizontal direction, 4 in the vertical direction, and we can draw another vector that is equivalent to the one that we started with. Looking at all of them, then we can see then that they have the same magnitude and they all go in the same direction. Let's look at one more example. Here we have 2 points, the point 1, 4 and the point 5, negative 1, and we want to connect them with a vector and then find a position vector that's equivalent to the vector PQ. So one thing to note here is that the vector is written as PQ with an arrow over it, which tells us that the point P, which is 1, 4, is the beginning point of our vector, and the point Q, which is 5, negative 1, is going to be the terminal point of our vector. In other words, our vector goes in the downward direction. So this is the vector PQ. And we want to write a vector that is equivalent to that, but is a position vector. So notice that we can determine the horizontal component of PQ. This is going to be our V1. The horizontal component is going to be the horizontal direction of Q minus the horizontal direction of P, 5 minus 1, which gives us 4. Similarly, the vertical component of our vector, V2, is going to be the vertical component of Q, the negative 1, minus the vertical component of P, which is 4, and we get negative 5. So we know that we can write PQ equivalent to the vector V, which is the vector 4, negative 5. That vector as a position vector would look like there's the point 4, negative 5. And so our vector V as a position vector is this one here. Reflecting on the main ideas that we've covered here, we know that vectors are quantities that have both magnitude and direction. The components of a vector are going to describe its directional change in both the horizontal and vertical directions, so that we can have a number of vectors across the plane that are all represented by the same components and are all equivalent to the same position vector. We use the Pythagorean Theorem to determine the magnitude of a vector, and we'll see as we go on that vectors underpin all of the work that we do in Calculus 3. Taking a look at what's next, we'll be exploring the idea of unit vectors as well as the direction of vectors, examining vector operations to combine vectors together as well as change their magnitudes, and we'll be expanding all of these ideas into 3 dimensions.